Support vector machines. Support vector machines is an algorithm that determines the best decision boundary between vectors that belong to a given group or category and vectors that do not belong to it. It can be applied to any kind of vectors which encode any kind of data. This means that in order to leverage the power of SVM text classification, texts have to be transformed into vectors. Now, what are vectors, you may ask? Vectors are lists of numbers which represent a set of coordinates in some space. So when SVM determines the decision boundary, as we mentioned above, the SVM decides where to draw the best line or the best hyperplane that divides the space into subspaces. One for the vectors that belong to a given category, and one for the vectors that do not belong to a given category when the number of subclasses are 2. Now, in our text classification model, since there will be 5 different categories, there will be the boundaries. The boundaries will be drawn at the intersection of the 2 categories to separate the categories. So, provided we can find vector representations which encode as much information from our texts as possible, we will be able to apply SEM algorithm to text classification problems and obtain very good results. We now have the support vector machine model. The same, we import the necessary packages and libraries and we load the data. And for the cross validation for hyperparameter tuning, we have the following hyperparameters, that is cache size, class weight, decision function shape, degree, gamma, kernel, maximum number of iterations, probability, and so on. We see that we have 14 parameters currently in use, but we will be focusing on hyper tuning the 4 parameters. That is C, which is the penalty parameter C of the error term, kernel, that is, it specifies the kernel type to be used in the algorithm, gamma, which is the kernel coefficient, degree, which is the degree of the polynomial kernel function. Now, to form the randomized search cross validation, we first need to define the grid. Define the grid for the parameters we are tuning, that is C, gamma, degree, kernel, and probability. Then we perform the random search by fitting 3 folds for each of the 50 candidates, totaling 150 fits. The best hyperparameters from the random search are found that it's possible when probability is true, kernel is poly, gamma is 10, degree is 4, and the value of C is 0.01. The mean accuracy of this model with these hyperparameters is 92.12%. After that, we do a more exhaustive search centered in those values. Now, fitting the model for 3 folds for 28 candidates, totaling 84 fits, we find that the hyperparameter value is 94.98%, which is considerably higher than the previous one where we found it to be 92%, 92.12 to be precise. And this 94.98% accuracy was found when the value of C was zero point 0.1 instead of 0.01 which was used earlier, and the kernel value was linear instead of poly, and the probability value remained true. This was the best result for the SVM model. Let us now see how it performs. Model fit and performance. We fit the model for the trained features and trained labels and get the prediction for the test class. The conditional class probabilities can be obtained by typing svc pred, which was similar to RFC pred, which stood for random forest classifier in the previous model, but here svc stands for svm classifier. But since it's a support vector, we just use SV classifier, the support vector classifier, and drop out the word machine. For performance analysis, we will use the confusion matrix and the classification report and the accuracy on both the training and the test data. On the training data, the accuracy was found to be 95.92%, but the training accuracy in a random forest classifier was found to be 100%. The test accuracy for support vector machine is found to be 94%. If we look at the classification report, we see that there is a range of values for precision. It is 88%, 96%, 97%, 99%, and 93%. Averaging it out, we get the value of 94%, recall as 94%, F1 score as 94%, and the support value as 334. We see that the precision, recall, and F1 score averages is greater than the one which we had in the previous model, that is a random forest classifier, which had 93%. Here we have 94%. Then we form the confusion matrix, where business has a value of 79, entertainment 46, politics 64, sports 71, and technology at 54. At this point, we could get the average time the model takes to get predictions. We want the algorithm to be fast since we are creating a model that performs best with respect to the baseline classifier. We see that the model performs a training set accuracy of 95%, 95.92%, and a test set accuracy of 94%.